So hello everyone, welcome to the Ask IITians YouTube channel. And today we are going to actually talk about one of the very important chapter, which is called the coordination chemistry. Now you can understand that those who are preparing for JEE and all, guys, this particular video is not for serving the purpose of JEE. Here I'll be mainly making this video in order to help the students, those who are going for their school examinations or for the board examinations. So we'll be talking about all the details which is there in the NCERT. In fact, what we'll be doing is, guys, we'll be going line by line through the NCERT and we will be trying to understand everything which is written on. For the JEE preparation or the JEE advanced preparation, guys, that we'll be doing in the classes like we always do. And right now, the main purpose would be, again, I'm telling you here, if you are here in this channel just to understand up to the boards level and only the things which is written in the NCERT, then guys, you can watch the entire recording here, entire video here. And also I would suggest you, if you feel like is any of the topics you know about it, you can just skip that part and you can jump to the next topic. All the thumbnails of all the portions will be given in the descriptions as well. So let's come to the point now. So here first what we are going to discuss about is the all important pocket vision of this topic, okay, from where the questions are going to come. On the top of it, guys, we'll be again in the books there are certain things where the parts are not clearly being defined, okay, so that part is also something that we are going to go through. From the JEE mains topic, there is only one thing that I'm considering today, guys, which is the carbonyl molecular orbital diagram. It has been seen that over the period of time, many of you have issues with the carbonyl molecular orbital diagram. So I'm taking that into consideration as well. So mainly these are the overall things that we will be discussing about. The entire chapter would be taught in this particular video only. We'll be having some breaks in between, but our main target would be completing the entire chapter in detail in today's video. All right. So let's get started with the topic here now. Okay. I hope I am sharing my screen properly here. Let me check once. Right, everything seems perfect. Zoom in a bit. Okay, guys. So before we get started with the topic here, first there are certain things that I would teach you here, so that you get a proper understanding about this chapter. Okay. Now the first thing over here, that is the most important part, that is regarding understanding the coordination compounds. Okay. Let me spotlight myself. All the settings are done now. We can come back to the point again. Now, like I was saying, guys, first we have to understand what is a coordination compound. Now, in coordination compound, we get to see a lot of coordination bonding happen, right? So let's say I asked you what is an ionic compound. There you see ions, right? Let's say I told you that give me an example of an ionic compound. So you would say, sir, KCl, NaCl, whenever there's a metal non-metal bond. For coordination compounds also, guys, we can have these kind of definitions. But let's say I asked you, what is this NH4Cl compound? In which category are you gonna put it under, right? In that situation, what you're gonna say, that sir, there are multiple kind of bonding present in it, right? Some of you would say, sir, it's an ionic compound. Why? Because it is NH4 plus. Yes, that's the right thing. This particular segment is definitely ionic compound. It's ionic bonding. Okay. Now, if you notice now, after that, if I break NH4 plus now, so in that case, what are you gonna do? So NH4 plus would be, let me break it down. H, H. Now this NH4 plus, how many types of bonding do you see, guys? This particular bond is covalent bond, and this particular bond is coordinate bond. Now, what I'm trying to tell you is, guys, when we are talking about coordination chemistry, don't think like the entire molecule would be only coordinate bond. That's never gonna happen. There'll be more than coordinate bonding present in there. Okay, this is something we have to keep in our mind. Now the question comes, what is a coordinate covalent bond, and why do we call it coordinate covalent? Why don't we just call it coordinate bond? So guys, it's like a very simple thing. There would be a, so in here, there would be a donor, there will be a donor molecule, and there will be an acceptor. Both the types of molecules would be donor molecule, acceptor. When I say donor molecules, they can be of many types. I'm going to teach you in detail about them. These donor molecules, we are going to call them in this chapter as the ligands. And acceptor molecules over here, or the acceptor elements or atoms, whatever you say, guys. In this chapter, they are going to be metals. Now, yes, you heard me right, guys. Metals are going to be acceptor. Achha, what are the donor, what are the acceptor, guys? What are they donating, what are they accepting? They're donating electrons, they're accepting electrons of it. Now the question comes, how can a metal become an acceptor? So I'm going to give you examples, and I'm going to give you a clarity in that particular topic as well. How can a metal accepting electron? But remember one thing, here the acceptor metals are mostly the d block metals. Not only mostly, I should say only the d block metals. Because of d block metals have multiple vacant orbitals. Because of that, we can consider them as the acceptor orbitals. This much we are all clear, I guess. Now, let's get into deeper down into this topic. Now, guys, who are the ligands? Who are the donors? See, the donors are of two types. One are the anionic donors, means the negatively charged donors, and the other one are neutral. These two types of donor atoms will be found. There will be some situations where you are going to get cationic donor as well, like hydrazinium ion. So in these kind of cases, they are not in our, like I said, these are not in our board syllabus. I'm not going to teach you. Board or JEE main syllabus, it is not there. But there are people like, nitrosonium ion, hydrazinium ion, these kind of things are there. Okay, nitronium ion. So when we are going to learn about them, you're going to see that they're cationic but yet donor. Okay. Now, mainly we are going to talk about anionic and neutral. Guys, see, they are donating electrons. That means, guys, in organic chemistry, you have also heard about them in terms of nucleophiles, I guess. You remember? Nucleophiles were the same things now. Those who used to donate electrons, somebody. They are the nucleophiles. Now, just like the nucleophiles are also two types, anionic and neutral, here also we have the same kind of classifications. And we're exactly going to talk about the nucleophiles here as well. So what are the anionic nucleophiles? I mean, like I said over here, they're just the same thing, right? We can call it a nucleophile as well. So what are the anionic ligands present in here? Anybody with a negative charge. Anyone with a negative charge is an anionic ligand. So Cl minus chloride, Br minus bromide, I minus iodide, etc., etc. Okay, these are all anionic ligands. When we talk about, here let me give you one more example. Like all the nucleophiles and the ligands are the same thing. Cl minus, then what else? Cyanide, Mc minus. These kind of people are all your anion nucleophiles. SCN minus, NCS minus, etc. Anybody with a negative charge. Now, when we come to the next part, which is the neutral. Neutral but yet donor. How's that possible? Guys, if a neutral element has excess electron. I shouldn't say excess lone pair, guys, because lone pairs are always the excess electron. Correct? So you should rather say excess electrons in terms of lone pairs. In terms of lone pairs. Then they are also your ligands. They are also donor atoms. Example: ammonia, nitrogen, water, oxygen, 2 lone pairs. What else? Ethanol. You try to give an example now. Try to think about one. See, ammonia and ammonia derivatives are all gonna be in the same. Then we have carbon monoxide. We are gonna call it carbonyl. This is also there. Then we have nitrosyl. That is also there. Now you have noticed that for every one of them I have shown you the donor atoms. But here for carbonyl and nitrosyl I did. Because if I do, that would be a controversial thing right away. Okay, and you'd be having a lot of questions right now in your head. So that part I'm keeping for the carbonyl MO, like I told you. I'm gonna teach you in the end of the session. So you're gonna keep it for that time, right? Now, so this was your understanding about the donor atoms. So you have anionic, you have. This is just the beginning. You know, there are more actually. There are monodentate, bidentate, tridentate, hexadentate. We're gonna talk about. So these are the names. Now let's talk about one more name. You know, they have another name actually. Nucleophile, ligand, and they have another name. What are the other name, guys? They are all Lewis. Lewis what? Lewis bases. They are all Lewis bases present. I guess we are clear up to this stage. Okay. Now, coming to the next part. The metals. Why are the metals being chosen here? And why are the acceptors? Let's answer both the questions here now. So now see, if I talk about the metals, they are actually the D block metals which I informed you earlier. Which all kind of metals are we going to see here? We are going to see iron with a +2 state, iron with a +3 state. Then we can see copper with a +1 or a +2 state, both you can see. Ni in 0 state or Ni in +2 state. See, long story short, if you are somebody who have gone through DNF block chapter, you know it by now, guys, that every D orbital, every D block element, 3D series I'm saying, like the first D series, okay? So in there, you'll be able to see, you have learned it in the DNF block, that every one of them are stable in +2 oxidation state. So you can consider that. Every one of the D block elements with a +2 oxidation state. But why are they being chosen? Why are they accepting electrons? Because of the plus charge? No. Sodium also have a plus charge. Are they also accepted? No, they are not. Why are these people accepting electrons? Because, guys, they have vacant D orbitals. Because they have vacant D orbitals. When we'll be going into the bonding part, you'll be able to see this thing even more. What is the vacant D orbital? How does it work? All right. But right now, the exception is, the point is, as they have vacant D orbital, they are all very good acceptors, electron acceptors. So now this is a story so far. But the point is it only the metals of D block orbitals or those who can make this kind of bonding? Does it always have to be like that? The answer is no. We have just seen an example before we started all this, isn't it? NH4+. If you notice, guys, this is also the similar kind of example. How? Ammonia, you know that, guys, this is our donor atom, right? This is our donor atom. If this is our donor atom, that means you can see that because it has a lone pair of electron, that's why it's a donor atom. So this is my ligand. What kind of ligand, guys? Neutral ligand, or I should call it a Lewis base, all the same things, right? You can call it a neutral nucleophile as well, same things. Now, let's say I am treating this with a little bit of acid, H+. Guys, see, H+ is a classical beggar of chemistry. Why do I call it a beggar? Because just like a beggar, it has no electrons in its shell. A beggar has no electron in his bank account, right? No electrons means no money in his bank account. Similarly, here also you have no such electrons in your shell. That means, guys, you can always come to this understanding that if you do not have any electrons, then definitely, in order to fulfill your shell, you are definitely going to take electrons from somebody who has it. Just like a beggar, he goes to a rich person, and the rich person can stabilize him by giving him some money. Right? It's just like that. So you take the electrons, and what you do is you get a stabilize one s orbital, and now together you make this kind of bonding. It's like a kind of relationship that I say in the classes as well, guys. It's like when a rich person, the rich people are rich for a reason. They don't do anything like just because they feel about it. They do it because there is something that is in it for them as well, right? That's how they have this kind of mentality. That's why they're rich. That's what I believe, actually. Now, if they're giving money to some, he's gonna go to this offer. Like, see, you are begging anyway in the streets. Why don't you come and work for me? And I'm gonna make this regular wage for you. You'll be getting this kind of salary every single month, right? This is like the same thing. You can see that ammonia is not just letting the hydrogen go. He's going like, come and work with me. Join me, work with me. You can see that he has joined that. Now here's the best part. After you donate the money to the beggar, right? Similarly, ammonia has donated the electron to the beggar molecule, which is H+. The moment it happens, guys, till that time, we can understand it is covalent bonding. But after the bonding has formed, here, they make it look like a normal covalent bond only. It is not anything special after it has been formed. So it's like he just looks like a normal employee, right? He doesn't look like a beggar anymore. So it's like that. After you make this bonding, it is just a covalent. It behaves like a covalent and you cannot recognize. So that means, guys, what I'm trying to say is, in an NH4 plus molecule, you don't know which one was the beggar, which one was the H+. Whether it is this one or whether it is this one, whether it is this one or whether it is this one, you would never have any idea. It can be any one of them, but they are all equivalent, right? Okay, is that clear so far? Conclusion, what is the take home point here? Guys, the take home point is coordination bonding or coordinate bonding. You write it with me as well, guys. Coordinate bonding can be formed by a molecule or ion full of disposable electrons. Guys, this is not a definition. This is our take home point. Disposable electrons. Disposable electrons means excess electrons that you can dispose, you can give away to somebody. Full of disposable electrons. The coordination bonding can be formed by molecular disposable electrons with a molecule or ion with a vacant orbital. Guys, this is very, very important now. You have to have a vacant orbital in the acceptor segment. This is for the acceptor. Whoever would be the acceptor, you have to have a vacant orbital. Only then you can get it. So far we are clear? This is the entire thing. Now let's come to the point called the Werner's theory. This part is not mentioned at all in the book. Now from here onwards, I'm gonna refer to the book. I'm gonna show you where things are exactly written so that you can also read it side by side. Let's learn about the Werner's theory. Werner. Now, let's refer to the book, what is written in there, and then we'll be explaining that part, okay? Guys, whatever I'm teaching you, that is more than enough for your preparation, okay? Now see. In coordination compound, the metal shows two types of linkages or valencies, primary and secondary. So let's just read all the points first, then I'm gonna go back and explain this. So there are two types of valency, one is primary, one is secondary. The second thing they're saying that primary valences are normally ionizable and are satisfied by the negative ions. Then the third point is saying that the secondary valences are non-ionizable. These are satisfied by the neutral molecules of the negative ions. The secondary valency is equal to the coordination number. Very important statement of a fixed metal. Point number 4, they are saying that the ions of the groups bound by the secondary linkages to the metal have characteristic spatial arrangement corresponding to the different coordination numbers. Okay, let's understand what are they trying to say by these 4 statements. Okay. Now, let's try to understand the first point, which is they're saying that there are 2 types of valency. Okay. Now, guys, the valencies they are giving as primary, and the second is the secondary. Try to understand what are these 2 things. So, I would suggest you to remember what have you learned about valency. So, let's say what is valency if I asked. You would have been telling me 2 different kind of definitions over here. Definition number 1 is, sir, this is the combining capacity. Combining capacity. Like you can say, for oxygen, sir, we have seen that. Example, for oxygen, the combining capacity is 2. That's why the valency. How do we prove that? So if I look for water molecule, you can see that oxygen is combining with 2 hydrogens. That means it has 2 hands, just like all of us. And that's why the valency over here is 2. Well and good. You can say that for sure. That's what we have learned from the day 1 about valency. Or you can do another thing. You can say another thing. You can go for point number 2. What they are saying over here is the number of electrons accepted or donated during a chemical reaction. The number of electrons accepted or donated during a chemical reaction. That is also called your valence. Now, what do I mean by that? Let's say I'm talking about oxygen only. Now, guys, oxygen's electronic configuration, 1s2, 2s2, 2, 3, 4. Now, if I draw the valence shell, which is 2s2, to P4, this is the thing. Now you can see, guys, it would definitely try to take 2 electrons to make itself octet filled up or to make itself its p orbital filled. So as a result, guys, oxygen accepts 2 electrons. So that's why its valency is O2 minus, and the valency is -2. So guys, see, the valency can be described by more than one ways. One is the first one is the combining capacity. The second one over here, as you can see, that is the charge present on the atom, right? It can be positive, it can be negative, that's the difference. But it would be the valency. Now, in this chapter, generally, all the time we have been studying, we have found the same answer by both the definitions. But here in this chapter, guys, for the first time, you are going to see 2 different definitions, different values for these 2 different definitions. When you say about combining capacity, guys, we are going to call it coordination number. Coordination number, which can be also called as the secondary valence. Means the number of elements with attaching breadth. That is called a secondary valence here. Okay. Now, the second one, the thing that we have just learned about the ions and the charges, this is called the primary valence. Okay, this is called the primary. So these are the two things about it. Now, how are they different in a coordination compound? Now, to understand that, you have to know how to draw a coordination compound, how to understand the connectivity there, and then we can come to this. Okay. Now, let's try to understand how to draw a coordination compound. How to draw coordination how to draw a coordination compound. That's the question. Now, see, what we generally do whenever we are trying to show the coordination part, means, like I said, in a molecule you can have multiple type of bonding. You can have coordinate bonding, you can have covalent bonding, you can have ionic bonding present in the same molecule, like in each molecule, right? Now you see, when we are talking about that multiple kinds of bonding are there, for coordination chemistry chapter, guys, what we do is, whoever is undergoing the coordination bonding, we keep it in a square bracket. So inside the square bracket, whatever I write, they are all the part of coordination chemistry. They're all the part of coordination bonding. This much we are all clear. Now what we see over here is, let's say I'm giving you a random molecule, FeCN6. FeCN6. That's the question. That's the molecule. Where, guys, you can see in coordination chemistry, I told you there'd be an acceptor and there'd be a donor. Now over here, who's the donor? Definitely the cyanide. You know that, guys, that is the Cn minus, right? It's a negatively charged ligand, right? So there are these people, those who are the ligands. Yes or no? And when we talk about the ion, like I said, guys, it's a D block metal, right? It's gonna be your acceptor. This is gonna be your donor. This much we are fine. Now, as you can see, how many donor atoms do you see, guys? You see total 6 donor atoms are here. So if I ask you this question, what is the secondary valency of the compound of iron? Let's look like this, of Fe. What is the secondary valency of iron? Achha, by the way, guys, this is something I forgot to tell you. This primary and the secondary valency both are for iron only, or the metal atom. We get this. So what is it? What is the secondary valency for the iron over here? So like I said, guys, it is the combining capacity for the iron. How many atoms, how many molecules is it combined with right now? It's combined with 6. So the secondary valency, or the coordination number, we can also call it the same, right? That is 1. Okay. Now, here's the main thing. Okay. Now, guys, we know that iron can have 2 types of valence. One is +2 and the other one is +. When it is in +2, we call it asferous. When it is in +3, we call it ferric. It can have 2 valence. Now you can say, sir, which valence is being used here? +2 or +3? We are talking about charges now, guys. Why? Because I'm trying to find out the primary valence. Secondary valence, I guess we are all clear. Now the point is how to find out the primary valence. For that, what I'm going to do is, you know, iron can be in 2 ways, like Ik and Us. So it can be either of them. So for the time being, for understanding purposes, we are going to just take any one of them. Okay. Now you understand, I'm going to do the first, you're going to do the second. Let's say, guys, I am taking this one, +2. So iron's charge on the top of it is +2. Correct? It can be plus 3 or plus 2. It's plus 2. Let's consider. Now 6 cyanide. What is the charge of them? You can see 1 cyanide is containing 1 minus charge. So 6 cyanide would be containing 6 minus charge. Is simple. So what is the total charge on the square bracket over here? Minus 4. Total, adding them up. Total charge is minus 4. So now my question is, with this particular coordination compound, then it's a iron actually. It's an iron with a 4 minus charge. If I have to find out a neutral coordination compound out of it, then what do I have to do? I have to give a counter ion. Counter ion means, guys, if this is minus, I have to give somebody with a positive charge in order to neutralize it. Now you can choose anybody. Let's say I'm choosing potassium. Guys, for potassium, the charge is 1 plus 1. So if for potassium the charge is plus 1, and for FeCN6, which is the anionic part, it has the charge of minus 4. So if you cross multiply it like you have learned in your junior grades, so the compound that comes forming is K4 Fe6. Now guys, understand this part very well. This potassium over here is actually in between these potassium and the coordination sphere. The kind of bonding which is there is ionic, and here inside it is called coordinate. Understood? So like I said, there can be multiple type of bonding. In order to stabilize the molecule, I'm doing a ionic bonding. This particular square bracket is also famously known as the coordination sphere. Coordination sphere. So this is the main thing. Now guys, coming back to the point. So this is how you get the total compound. Now I'm going to give you a question. You try to solve this. If iron was plus 3, if iron was plus 3, then FeCN6, 4 minus, I guess I don't have to teach you that. Okay, no, let's figure it out. Okay, FeCN6 is your anion, and the cation would be, let's give sodium. So guys, what will be the form? What will be the correct form of the compound? Come on, give it a try. Okay, I guess you are all tried. If you haven't tried it yet, guys, just pause the video and watch it and try to figure it out on your own. Sodium is plus 1, that is something that we all know. Now iron, over here it is in plus 3 oxidation state, I told you before on ferric. Now cyanide, 6 cyanide is minus 6. Each is minus 1, so 6 would be minus 6. Minus 6 plus 3 is overall minus 3. So how many sodium do I need in this situation, guys? Na3 FeC. That's the compound. Understood, guys? So you have both ionic compound as well as covalent coordinate compound in this kind of. This particular molecule, the one who is there to neutralize the molecule, they are called the counter ions. Okay, so this is the entire part. They're called the counter. Now, when coming to the question, primary valency. What is the primary valency? Now, like I told you guys, primary valency is this charge on iron. Like for this question, the charge on iron is plus 3, so that is the primary. And the previous question, what was the charge on iron? If you notice, that was plus 2. So primary valency over here is plus. So it's the charge on that. That's called the primary. Okay, guys, clear so far? Okay. Now I suggest you to take a short break and come back. This is one of the topic got covered up. Now we'll be moving on to the Warner's next theories and all. And after that, we'll be solving one or two questions from the NCERT as well. Take a short break and come back from there. Okay. All right, guys, I guess you're all back from a small break now. So let's get going from here. So we have learned about the primary and the secondary valency. Let's go for a quick overview of the entire topic here now. Let's solve one question to understand this thing. Let's say, guys, I'm gonna make you a compound, okay, which goes like this. You have, okay, the metal over here is cobalt, okay, cobalt. You are combining this guy with ammonia. 4 of them are ammonia, 2 of them are chlorine, right? And I have enclosed them in the bracket. The question is, if I consider the charge of cobalt over here is +2, that means, guys, in a way I'm saying the primary valence is. Now, if I'm asking you, what is the secondary valency here? And I'm also asking you, if the counter ion is, I'm just making it up, guys. We never really see these kind of compounds though. But let's say the counter ion is aluminium, right? So what would be the formula of the entire compound? That's the question. We pause this video right here and try to solve this question. So I hope all of you have tried this once before continuing for the solution here. So have a look now. If cobalt is in +2, what is the charge offered by ammonia now? Guys, ammonia, if you remember, that was a part of a neutral ligand. It used to donate its lone pair. So as a result, ammonia offers no such charges. That is just 0. Chlorine, it is, guys, chloride ion Cl-. So you can understand that each of the chlorine is -1 to total is -2. So then, what is the total charge of this compound over here then, guys? The overall charge of this compound is coming to be +2, 0, -2. If you add them up, the overall charge is 0. That means, guys, this particular coordination species is a neutral one. So there would be no such counter ion needed. Right? Counter ions, what are they? Why do we add them? Just to neutralize it, if you don't forget it yet. So to neutralize the system, we give the counter ions. Here the system is already neutral. So there is no point of giving counter ions here. Let's try one more question like that. Let's say we have a compound which goes like this. Na2CO NH3 whole twice, water whole twice, okay, and then we add Cl whole twice. Okay, by the way, I forgot to ask you what is the secondary valency of this. Guys, tell me what is the secondary valency of the central metal atom now here? That would be how many things connected with it. How many ligands are connected over here? 4 and 2, 6. The total, the secondary valency is 6. Now here goes the thing, guys. The secondary valency can be 2, can be 3, can be 4, can be 5, can be 6, can be 7, can be 8, it can be anything. But here is the thing about this chapter. As we are talking about boards level, remember that you are not gonna see a single compound more than 6 secondary valency. Okay? There are certain D block elements, like the heavy elements, right? Like silver, like mercury, like gold. What I'm trying to tell you is, guys, if you look at the D orbital, D block elements, what are they? This is the periodic table, right? Let's try to visualize the periodic table first. In the periodic table, you have seen one side of the periodic table, you have the S block element. The other side of the periodic table, guys, you have the P block elements. And in the middle, you have the D block. Correct? In that middle of the D block elements, what you have to do is you have to see that the first line of the D block elements are called 3D elements, then 4D, then 5D. Means scandium to zinc are actually 3D elements. Then after that, that means yttrium, right? Yttrium to their cadmium, that is called 4D elements. Because guys, if you write the electronic configuration, you'll be able to see that those elements last shell is 4D, right? And then beneath that, like lanthanum, there are 5D elements. It goes like that. Then the 6D element, it goes like that, right? Now the point is, I'm talking about right now, 3D elements are being given in your school examinations and in your books and in JEE mains. So there, guys, the highest coordination number you see is +6, okay, or 6. The second most given coordination number is 4. You would hardly see a coordination number 5 system, guys. There are few of them though, like there are ferrocene compounds, those who have 5 coordination number, but generally 4 and 6 is what you're gonna see. 99.99% times you're gonna see 4 or 6. Okay, 2 is also there. I'm not saying they are not gonna give you. They might give you, like AgCN2. They might give you this number, but it is very, very, very less likely to happen. All right. So this is the main thing now. So 4 and 6 is what you have to understand. So that's why I'm making most of the compound with 6, right? That too again. Now about the 4 coordination number, that is also not being shown by everyone. There are also some people only make it. Like copper can make it, like platinum can make it, right? There's no such reason behind it, guys. Platinum can make many coordination number. It can make 6 as well, it can make 4 as well. Same goes for nickel as well. So mainly, why do we see this coordination number? As you know, guys, after the formation of bond of those compounds, the stability and all these things are being judged, right? From there, the coordination number gets. Now I'm going to talk about coordination number even more into detail in the bonding part, right? Right now, let's just continue with this thing. So here we have seen that what happens is this is the compound given. So all you have to tell me is, guys, what is the primary valency of whom? Of cobalt, always the central metal atom, okay? And the secondary valency of the central. Give it a go. Pause this video, give it a try, and after that you play it. Okay, I guess by now you have completed it. So here goes the answer, guys. Acha, about secondary valency, that's the easier one. Inside the square bracket, the number of ligands accommodated by the central metal atom is gonna be called as the secondary valency or the coordination number. Same thing. So the coordination number of cobalt over here, guys, that is 2 of ammonia, 2 of water, 2 of cyanide. The total it is 6. Simple. What is the primary valency? Guys, if you remember the chapter redox, they are used to find out the oxidation number of a particular species. Remember? That's the same thing you have to do here. Let's say we know the oxidation number of sodium is +1. For one atom it is +1, right? Total it is +2. I'm gonna do that. For one atom it is +1. Now, ammonia, guys, what is the charge offered by ammonia? That is 0. Why? It is a neutral atom, right? It donates this lone pair. You have to remember this. Ammonia, water, alcohol, amine. You remember it from organic chemistry as well, correct? They are also, you're gonna see them. They are donating their lone pairs. These are neutral atoms, okay? So amine atoms is molecule here. This is also 0. Cyanide, is it also neutral? It is also neutral. It is not neutral. That means it is going to be -1 each. So guys, you have to understand the things in here. Cyanide is Cn-. There is a one shortcut that I'm going to give you. Pronounce the name. Ammonia, water, cyanide. If you notice, guys, whenever a ligand ends with a ide or ate, what are the things? Ide, IDE, ITE, AT. Whenever a ligand ends with an ide or ate, in those 3 situations, you can consider that it is going to be your anionic ligand, right? But yes, that would be difficult to understand whether it is -1 or -2 or -3. That, guys, you have to know for a fact. But generally, we can say that this is an anionic ligand, this is neutral ligand, this way, right? Ammonia has no ide. Let's say carbonyl, anion, cation, or neutral, right? Let's say nitrosyl, neutral, right? Let's say thiocyanide, anionic. Similarly, guys, when we go for cationic ligand, in J advanced classes, I'm going to teach you that. In cationic ligand, you're going to see in the name. Nitrosonium, hydrazinium, nitronium, hydronium, correct? And ammonium. These are, ammonium is not a ligand. Don't get me wrong here. I'm just, making a connection between and the cationic. Right? Now, coming back to the point again here. What is the primary valency? So count it now. Take your carbonyl as X. I mean cobalt. Okay. Cobalt as X. So guys, the total is plus 2 because 2 sodiums are there. Plus X plus 0 minus 2 because 2 cyanides. So guys, our overall charge over here is coming as plus 2 minus 2 cancels out. So X comes as 0. Yes, this can happen. The coordination compounds can have a metal with a primary valency 0. It is possible. Right now, the compound I have made, it is an arbitrary compound. But real compound can also have a 0 valency. For cobalt, although you don't see that much of 0 valent compound that much, but for nickel, you see many. Nickel carbonyl complexes are 0 valence compound, right? That is pretty normal. Okay. Now, coming back to the next part of it. So guys, I guess by now the valency part is entirely clear to all of us. This is a very, very important segment for us to understand here. Now, let me tell you. Okay. Now, let me tell you about the next Werner's theory. I guess in a way, guys, I have explained all the 3 Werner's. One is there are 2 types of valency. Second is secondary valency talk about the coordination number or the spatial arrangement of the system. And the primary valency talks about the charges present in the atom. Okay. Now, one thing, guys, which I have to tell you about the spatial arrangement. Spatial arrangement of a coordination compound. Okay, now here this is important, guys. Although I'm supposed to teach you this in the bonding segment, guys, but I don't think so it would harm you anyway if I tell you right now. Spatial arrangement of a coordination compound. Guys, you have been seeing that, and I've been telling you as well, you're going to see mainly 2 types of coordination number. Okay. Now, you have seen that in Werner's theory, they are saying that coordination number somehow determines the spatial arrangement of the compound, right? But how? Why are they saying that? Because, guys, see, on the basis of your coordination number, you can talk about the geometry. Like in bonding, we learned it. Whenever the coordination number, whenever the value of the number of ligands, or you can say, okay, in bonding, you have never learned the word ligand. Over there, you have learned like SF6. What would be the structure of this compound? What would be the geometry of this compound? You would have been going like, sir, SF6 is octahedral in nature, correct? You have learned it from VSEPR, VBT, correct? Hybridization and all those places. VSEPR mainly, you have learned about the octahedral species and stuff. Similarly, guys, here also we are going to learn about VBT, VSEPR and all those things in here. Molecular orbital theory and all those things. For 4 coordination number, we see 2 types of geometry. One is going to be called as the square planar. I'm going to explain these things into detail in the bonding side. And the other one is tetrahedral. Tetrahedral, I guess everybody knows, right? Coordination number 4 is tetrahedral, right? CH4 is tetrahedral, right? Similarly, square planar is something that might be a little bit new to you. Also, although in VSEPR you have learned about square planar, right? Let's say XPF. What is the compound? What is the geometry? Or what is the shape of it? What we used to do? We used to do like this. XZ over here, xenon. F, 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 F. Lone pair. Right? What is this structure? You used to learn this is called square planar. Now guys, this is not a rocket science. You can clearly understand it's a square and the square is in the same plane. That's called square planar. So this can be a coordination number 4, or in CH4, a tetrahedral shape, that can be also coordination number 4. Coordination number 6, that is always going to be octahedral. That's always going to be octahedral, like I have shown you here. So guys, all the species that we have been seeing so far in here, all of them are octahedral in geometry. That means that's how the secondary valence is going to decide what kind of geometry you have. Octahedral, square planar, tetrahedral, trigonal, bipyramidal. Like I said, coordination number 5 people are there, right? Ferrocene complex, like I've given you example. So they are trigonal, bipyramidal. Just same thing as coordination as the bonding you learned, right? 4 means tetrahedral you learned, 5 means TBP you learned, right? Same thing is over here. So that is how the spatial arrangement that the Warner's theory is saying. Let me show you here. There you go. First written somewhere here. Secondary metal have characteristics spatial arrangement. This is the spatial arrangement required. Right. So this is the entire part, guys, about the Warner's theory. Now, if you notice in this part, difference between a double salt and coordination complex. Very, very important in terms of school examination. Okay. Now, what is this double salt? What is this coordination compound? For that, I'm gonna take you to the right side of our notes once, and after this, guys, we'll be solving the Warner's theory questions as well in a minute. Okay. Let me down below a bit. Okay, this question is very, very important, guys. They do give you these kind of questions in school examination. So now you give heading as coordination compounds versus double salts. Okay, why the double salts are coming into the picture? Why are we learning to differentiate between them? What is the entire story behind it? That I'm going to tell you now. Okay, why is double salt being considered in the entire part? Double salts are being considered just because there are similar kind of arrangements are present in the double salt. So what are the double salts? When two salts are mixed together physically. Let's say I'm mixing K2SO4 with Al2SO4 whole thrice. When we mix them together, guys, there is a water of crystallization, 24H2O, let's say XH2O. There are places where it is written as 6H2O. Guys, what is this compound? This is called potash alum. Potash alum. Water of crystallization is generally said to be as 6H2O. There's something similar called more salt as well. There it is ammonium sulfate, which is there specifically. I'm going to talk about the formulas and everything. Now, if you look into this kind of compounds, over here, what is happening, guys? Potassium sulfate and aluminium sulfate are mixed together. That's called a double salt, right? So this is also a complex kind of salt. And if I'm talking about a coordination compound, guys, remember the process. First, you have to write the coordination sphere. Then you have to give a metal, some ligands of your choice, and then a counter ion. And how many counter ions would be there? That would be dependent on the charges present in the coordination sphere. So let's say we give this. This compound may be noticeable by many of you actually. This is something you have seen in your practicals. Potassium ferrocyanide, right? Prussian blue coloration. In the Prussian blue complex, we have learned about this compound. But anyway, if you haven't learned it, you're gonna learn it anyway in this year. So guys, what is the difference between these two compounds? They say that if you hydrolyze, means if you dissolve this coordination compound in water, what actually happens is, guys, you get the ionic part broken. This is the ionic part, isn't it? While teaching you the formation, I told you this. This is the ionic part. So the ionic part would be broken because water can break the ionic segments, correct? So the ionic part would be broken. But the thing inside the coordination sphere would never break into ions. Because, guys, they're not ionic compound. Come on, that's a simple thing. They're coordination compound, right? They're coordination bonds present in it. So that's why they do not break. Only the coordination sphere and the counter ions breaks. Only that happens. But if I talk about the double salt, here what happens is, guys, every single particle breaks up. So 2K plus is O2 minus, 2Al3 plus 3SO4 2 minus, Water, so anyway, it is dissolved in water only, so nothing to break in there, right? So this is the part about, guys, coordination compounds. So and double salt, they break into all the constituent ions, but the coordination compounds, they doesn't. That means, guys, you know what I'm trying to say. It's a very simple thing. If you don't consider it like we are learning coordination chemistry or something special about it, it's not actually. It's a very simple thing. Tell me one thing, guys. If I talk about water, water is made up of hydrogen and oxygen gases, right? Hydrogen is inflammable. Oxygen is supporter of combustion. When you combine them together and get water, is it inflammable? The answer is no. Is it a supporter of combustion? The answer is no. It's a new compound. Achha, guys, tell me one thing. If I have hydrogen and oxygen, which are the constituents of water, tell me one thing now. If I, do you remember the grade 10 thing that you learned? Identification test of hydrogen, what was it? It was like, if you take an incense stick or a, what was the exact word? I don't remember. If you have a incense stick or anything like that, burning sticks or anything, it would like light up with a pop sound, correct? Something like that was there. That was the hydrogen test. What was the test for oxygen, guys? Oxygen test was like this. It would, if you just take a burning candle inside the beaker full of oxygen, then it would keep burning, right? Something like that was there. Tell me, is water gonna give positive result in either of the tests? The answer is no, it doesn't. So that means, guys, similarly in coordination compound as well, if I give a iron test of iron in this compound, I will give a negative result. If I go for a test of cyanide system, then also I would get a negative result. So if I have to have a positive result, guys, I have to do the test for FeCN6 whole 4 minus. Only then it would be giving me a positive result. That means, guys, it's a compound. It doesn't have the constituents or the properties of either of the building block elements. Like FeCN6 has no such properties of iron, has no such properties of cyanide. Just like water doesn't carry any properties of hydrogen and oxygen. Am I making sense right now? Are we understanding this part? Okay. Guys, we can always, all the doubts that you have, you can always put it in the comment section of this YouTube video. And other than that, those who are my students, they can always ask me over the WhatsApp or over the class, right? Now, coming back to the point over here. So this part is the basic difference between coordination compounds and the double salts, which is being discussed over here. If I show you this part, guys, this question comes very often. So you're going to be getting this question here. So make sure you prepare this part with proper examples and everything, right? So more salt and potash alum are the two things, I guess, given in the book. Like I said, guys, I'll be referring to the book for every single thing here so that you can get a continuation over there as well. See. They have given carnallite, they have given more salt, potash alum, they have given KAl whole, it's a 4 whole twice. Guys, it's the same thing, okay? There is nothing new in it. Whatever I said, that is also potash alum. This is like they have combined both the compounds together and got a KAl whole 2SO4, something like that. But you can give this example like I've given as well. K2SO4, A2SO4 whole twice, and 12H2. That's the amount of water in there. Always refer to the book only, guys. Water crystallization is something that depends on the temperature and so many other points as well. You know that, right? So that's that. And you can see that over here. When dissolved in water, it breaks into the simple ions completely. But however, coordination compound FeCN6 4 minus of K4 FeCN6 do not associate into FeCN minus. Like I said, you cannot break it further. By dissolution, by chemical property, so you can break everybody. That's not a problem. Okay, so this was the entire thing, guys. Now let's try to understand the coordinates theory, whatever we have learned here. Let's try to understand what kind of questions are going to be given here. Okay, so let's get into the questions now. Just one second. Have a look. So what have they done is in this part of the question, they have told you that there is a complex with a molecular formula test. That's a coordination compound. It's a molecular formula is given. That means they're not telling you what is inside the square addition sphere, what is the counter, and they're not saying anything. They're just giving you the molecular formula. Fine. Now they're giving you an experimental result. What is the experimental results? moles of AgCl precipitated per mole of the compounds with excess AgNO3. That means what? It means like this is your compound. They are treating it with AgNO3 and they're getting the product of AgCl. How many moles of AgCl? That has been given. Right. See, in the first case, they are saying there are 2 moles of AgCl. So if you are getting 2 moles of AgCl, guys, now you try to understand this part. You are getting 2 moles of AgCl. See, AgNO3 is excess in amount. So 2 moles of AgCl, how is it coming? How is it possibly come? How can it possibly come? Only it can come only when this compound of mine have 2 chlorines outside of the coordination sphere. Understand this, guys. When a coordination compound is broken, you cannot break the people inside the coordination sphere. So the ions that would be formed is this entire part separate and the 2 chlorines separate. Now, if you do not have 2 chlorines outside of the coordination sphere, you can never get 2 moles of AgCl. Because to get 2 moles of AgCl, you need 2 moles of chlorine, na? Common sense. You need 2 moles of chlorine. Now, 2 moles of chlorine should be there in the solution. How can 2 moles of chlorine be there in the solution? Only if 2 moles of chlorines are outside of my coordination sphere. Because when they break into ion, they break like this coordination compound, like this. Okay, there is one new thing, guys, that you have noticed right now. That counter ion, all the time, all the examples I've given you, they were the cations. Here you can see that counter ion is coming as an anion. That can also happen. It depends on the charge of the coordination sphere. Guys. There is nothing new in it. Try to understand. If the charge of the coordination sphere is minus, then your counter ion would be plus. If your charge of the coordination sphere is plus, then your counter ion would be minus. Because, guys, counter ion is coming there to neutralize the element. So whatever is the charge of the coordination sphere, counter ion would be having opposite charge. Right? Example you'll be able to see right here. So that means, guys, in this compound with palladium, what can be the valence? What can be the compound over here? See, palladium would be inside the coordination sphere. 2 chlorine would be outside of the coordination sphere. So what else are there, guys? 4 ammonia. So you write 4 ammonia inside. This is the coordination number. That's all. Coordination number over here is coming as 4. That is the secondary valency. That's your answer. When this compound breaks, tell me how would it break? PDNH3 whole 2 plus, whole 4. This entire thing. 2 plus. Why 2 plus? Because 2 chlorines are there. Plus 2Cl minus. These 2Cl minus would react with AgNO3 to give you how many moles of AgCl now would form? 2 moles of AgCl. If you're saying, sir, AgNO3 to 1 mole, so I would show you that they're writing AgNO3 is not 1 mole, AgNO3 is given in excess amount. So you have unlimited amount of mole of AgNO3. So that is the problem. This is your compound, guys. Okay, they're asking for secondary valency. I'm asking for the compound kotor. So that would be this. Right? I hope you have all understood this part. Let's try to solve another question. Then it would be clearer. Let's try to solve the next one here. Tell me, guys, in the next question they are saying, let me zoom in a little bit for all of you. Okay. Now you try to solve this one. For this compound, they are getting 2 moles of AgCl again. That means how many chlorines are outside of the sphere, guys? 2. Whatever is the number of moles of AgCl you get, that is the number of chlorine outside, right? 2 chlorines are outside. That means rest of them are inside, right? NiH. That's the compound. What is the coordination number? Sphere coordination number, guys? Secondary valency would be your answer. Are we understanding this part, guys, now? One thing. Whenever you see that the coordination number is exceeding 6, you cannot do that, guys. Okay. Like I told you in this chapter, they would eventually give you a question where the coordination number is only up to 6. If you see more than 6 elements, you have to put it inside the square bracket, guys. You don't have to do that. You can put it outside of the square bracket. I'm going to give you 2 examples of that as well. Okay, now let's go for the next one here. This question is showing that you have 0 moles of AgCl. That means there is nobody who is outside of the coordination sphere. That means, guys, what would be the compound then? Put everyone inside. So PT Cl4 2H2. HCl whole twice like this. That's your compound. Okay. There is another way you can write it. It is HCl, right? So you can write it as H2PtCl6. I hope you understood what I did right now. What I did is I broke HCl. HCl being a polar covalent compound, guys, we can break it into H plus and Cl minus. Right? Now, a plus charge element cannot be a ligand because, like I said, yeah, there are exceptions. That is in the JEE Advanced we are going to learn. But a plus charge element cannot be a electron donor, right? They do not have any electrons. H plus specifically has no electron. So I'm only giving 2 chlorines inside from here. They can be very good ligand. So I'm keeping the H pluses outside as a counter ion. So H2PtCl6. This should be the right answer, okay? Not this one. This would be the right answer. Okay. So this is the thing. Now let's go for the next one here now. You try to solve it. You have COCl3 4NH3, but that is only giving you 1 mole of AgCl, right? So if it is giving 1 mole of AgCl, then outside of the coordination sphere, guys, how many chlorines are there? Come on, try it. 1. Rest of them are inside. Put everybody inside. You would always see that they would add up to 6. 6 or 2. This is your problem. Next, guys, go for the last one. Here also you can see 0. That means nobody is outside of the coordination sphere. None of the chlorines. 2. That's your coordination compound. Okay, by the way, for this question, guys, the coordination number is 6. For this question, the coordination number is 4. This and this. Okay. The H2PtCl6, you have seen that they have also total 6 ligands connected. I hope these kind of questions are clear, guys. These are the kind of questions they are definitely gonna give you. Okay, so I hope this part is clear to all of us. Perfect. Now, let's go for the next part. Which is the types of ligands. Okay, let's give it a heading of the types of ligand. Types of ligands. Guys, see, the ligands now, they have a specific thing about them. When we talk about the ligands, they say it like the ligands are connecting with the elements in the same way the way we bite someone. Right, the way we bite someone. So I'm not asking you to bite someone right now to understand how are they connecting with it. But it's like, they say, just the way, let's say there's a piece of sandwich. The way you bite the piece of sandwich, the same way the ligand connects with the metal. Now, from where is this analogy coming? This part it's a little deep. I'm going to show you about this part. So types of ligands, guys. That's why, they say that there's a term called denticity here. Let me change the color. There's something called denticity here. Denticity. Now, what is the denticity over here? The number of, note it down along with me, guys. The number of donor sites present in a ligand. The number of donor sites present in a ligand is called its denticity. It's called its denticity. Number of donor site. You heard me right. What I meant to say is, guys, yeah, every single time we have been seeing that ligands have only one donor site, but there can be multiple donor sites present. Examples? Let's say we go for monodentate ligand. monodentate. Dent is coming from the teeth. Like I said, we compare it with biting people, right? Monodentate. Here you're gonna see that the ligands have only one donor site. The ligands over here have only one donor site. That's why we call it a monodentate. Correct. Now, let's go for an example here. Example. Every example that I've given you so far, guys, they're all monodentate. Like ammonia. Who's the donor atom here? Nitrogen. How many of them are there in ammonia? Only nitrogen. That's monodentate. Let's go for Cl minus. Who's the donor? Fluorine. How many donors are there? Only one. That's why monodentate. Then we go for, let's say, Cn minus, don't go for it. It comes under a different kind of denticity. Let's go for anybody else. I minus, another halogen. These are all monodentate. Okay. Now let's go for the bidentate ligand over here now. Let's go for bidentate. Bidentate. What about them, guys? You can understand they have two donor site. In one ligand, you have two donor site. In a ligand. In one ligand, you have two donor sites. Right? This is something that you're gonna hear for the first time. Now, write down the examples with me. One is ethylene. Ethylene diamine. Guys, two ammonia segments are there. I'm going to draw the structures in a minute. Ethylene diamine. Then you write oxalate. Then you write glycinate. Then you write dimethylglyoxime, DMG. Okay, nickel DMG complex. You're going to see it in the practical chemistry. There will be many nickel DMG complexes discussed in that part. Okay, that is there. DMG. There can be many of them actually. Okay, I'm gonna just give this much for you, etc. etc. Am I missing anybody important? Ethylene diamine, oxalate, glycinate, DMG. No, I guess this is fine. Okay. Right. Now let's draw their structures here. Ethylene diamine, as the name suggests you guys, ethylene is CH2 double bond CH. But diamine, that means it is doing an addition reaction with two ammonia molecules, right? So addition, 1 NH2, 2 NH2. 1 NH2 has lone pair, so 2 NH2 has two lone pairs. So guys, it's a bidentate ligand because a metal, which is an acceptor, they can be donated by two sides. So ethylene diamine is a very, very famous bidentate. Now let's come to oxalate. Guys, this molecule is oxalic acid. COOH, COOH. This is oxalic acid. Now, oxalate, that means guys, like I taught you, it has to be a negatively charged system. You can see that it has also two sides to connect with the metal. Guys, I guess this is not confusing to you. The metals can be positive, the metals can be neutral as well, right? Like nickel, I told you. So it's also bidentate ligand. Glycinate. Glycine is the simplest form of an amino acid. This is glycine. Amino acid, like I said. So amino and the acid groups will be there. Glycinate, anion. Two donor site. One is nitrogen's lone pair, another one is carboxylic acid's negative. DMG, dimethylglyoxime. Okay, if you have learned aldehyde ketones carboxylic acid chapter, guys, then you probably know what is an oxime. If you don't, let's write after. Oxime is this compound. I don't need a hydrogen. C double bonded N. Then aldehyde ketone carboxylic acid chapter, guys, you're gonna learn that when a carbonyl compound is reacted with a hydroxylamine, we get an oxime structure. Okay. Glyoxime. Gly means di. Gly and di. Ethylene glycol means ethylene diol. Right? Similarly, if you have OH over here, guys, it is ethylene glycol or ethylene diol. That would also be a bidentate ligand. Similarly, glyoxime means dioxime. Same thing. Two oxime groups are there. This one group is called oxime. So now, dimethyl. There's methyl one. There's methyl another. This is the dimethyl trimethyl system. Donor atoms. Here, for a fact, guys, I'm going to tell you these are the donor atoms. Later on, I'm going to show you the structure. The nitrogen's lone pair, not the oxygen's lone pair. The nitrogens. They are the. From the common sense also, you can understand because of the electronegativity, nitrogen's electronegativity is less than the oxygen. In that way, also, you can understand this part. I hope you are all clear up to this segment, guys. These are all bidentate ligands because they can connect with the metal from two sides, right? Now, guys, they are not always given in terms of full names or in terms of structures. What they sometimes do is they use the abbreviation. Ethylene diamine has an abbreviation of EN. Oxalate is OX or C2O4 2-. Both of the abbreviations are being used. Glycinate is goes by the name of Gly. Okay. DMG, it's an abbreviation, I guess. Dimethyl glyoxime. It's anyway an abbreviation. Let me write down the name instead. Dimethyl glyoxime or dimethyl dioxime. Di and gly are the same thing. But don't write dioxime. Glyoxime is the right name. So these are the more or less these are the bidentate ligands that are. Similarly, guys, now we have, according to the NCERT, we don't have tridentate, tetradentate. They are not there. You have eventually all the way to the hexadentate ligand. So let's go for an example of a hexadentate ligand. Give the heading of hexadentate ligand. I hope you understand. Hexadentate means how many donor sites are there, guys? Come on. 6 donor sites are present in one compound. 6 donor sites are present in one compound, right? Simple. So now, how would it look like? How would the compound look like? See. The name of this example, there's only one of them here, right? Only one in the syllabus. That goes by the name of EDTA. In analytical chemistry, guys, that is something that we learn in masters, analytical chemistry. That means when we are trying to figure out the amount of a particular ion present in a compound, that's called analytical chemistry. Why do we need it? Let's say I am having a paint company. I want to understand what is the composition of this paint. Let's say I own a Berger paints, right? What's the composition of a paint produced by Asian paints? Let's say I want to make a competitive, let's say, product. What Asian paints have recently launched in the market. I want to launch the same kind of product in the market. Let's say, example. So in there, guys, what we do is we perform analytical chemistry. That means that tells you exactly how much amount of which component is being mixed in here. EDTA helps us in that, in analytical chemistry. One is this, and in nickel DMG complex in DMG also helps us in the analytical chemistry. Okay, guys, gravimetric analysis. For DMG, we go for gravimetric analysis. EDTA is also used in gravimetric analysis. Now, this EDTA full form is ethylene diamine tetraacetate. Ethylene diamine tetraacetate. Now, what is about them? So, try to form the compound first. Ethylene diamine, I guess, guys, we know the structure. EN, NH2 and NH2, ethylene diamine. After that, tetraacetate. Now see, this is the point. Acha, don't draw it in this way. Draw it in this way. CH2, CH2, N. Guys, I'm not drawing the hydrogens for a reason. Tetraacetate. The hydrogens are being substituted with the acetate group. Now, what is an acetate group? CH3COOH. What do we call it? We call it acetic acid. If I take out a hydrogen from here, anion, guys, acetate, acetate. Tetraacetate means 4 of them are connected here. So CH2COO minus, that means I am substituting one of the hydrogen with the group, argon, I mean the nitrogen. CH2COO minus. I'm not gonna draw the CH2 anymore. COO minus. Just showing you all the possibilities of drawing this compound in the bonding format as well. Why is it hexadentate? 1, 2. 2 donor atoms, 3, 4 donor atoms, 5, 6 donor atoms in one compound. Okay. So let's try some questions from this. Acha, one thing that I want you to notice once. Let's look at the structure of the ligands. Oh, by mistake, I have kept a lot of space in between. Isn't it? Okay, have a look, guys. Here. In this compound, I want you to look at their charges. Ethylene diamine is chargeless. It has no charges. It's a neutral ligand. When you look at the oxalate, I have already shown you guys, it has a -2 charge. For glycinate, what is the total charge, guys? The total charge is -1. Do you see that? Only O minus. For dimethyl glyoxime also, the total charge is 0. Okay, this is one thing I want you to do. Okay, coming back to the questions. Okay, there is one type of ligands I forgot to teach you. Let me put that as well. There's one thing called ambidentate ligand, just like ambidentate nucleophile. Ambidentate. Guys, ambidentate means ambiguous density. Ambiguous density. Now, what is the meaning behind ambiguity, guys? Exactly the way it sounds. Ambiguous density means indecisive density. Okay, means it can be like overall the ambidentate ligands are generally considered as monodentate. They're kind of monodentate. Example, let's say I have cyanide. You know the structure of cyanide is this. Now you have a lone pair of nitrogen as well. So guys, it looks like a bidentate ligand. But the point is, at a time it can give electrons from only one side. Means either this or this. Not and or. So either you're going to get one compound where carbon is donating electron, or you're going to get another compound where the nitrogen. For example, remember in organic chemistry you learned that whenever KCN is given, you get cyanide, and whenever AgCN is given, you get what? Isocyanide, isn't it, guys? It's the same thing. When the carbon center attacks, we call it cyanide. When the nitrogen center attacks, we call it isocyanide. Okay. So this is the main thing. Similarly, we have SCN minus or NCS. If you are attacking from the nitrogen side, guys, we call it, just 1 second. Okay. When you attack from the sulfur side, let's talk about this first. When you attack on the sulfur side, that time we call it thiocyanide. See guys, it's nothing difficult. You have CN already. A stands for thio, thiol, SO, SOH, thiol, right? Thio means sulfur, azo means nitrogen, correct? Similarly, thiocyanide. And what about this? Like cyanide and isocyanide, similarly, thiocyanide and isothiocyanide. Just add isothiocyanide. These are the compounds. Okay, guys, this much is clear. Now, this is thing, and for advanced now, there is not advanced in JEE mains level also we learn another thing which is called flexidentate ligand, which has flexible denticity based on the pH of that particular solution. If the pH is changed, it can show +6, it can show +4. That is EDTA only one of the flexidentate ligand that I'm gonna teach you in the JEE mains classes of the advanced. So I guess the denticity at the ligand segment is clear to all of us now. Now let's solve a few questions here from the ligand segment. Okay, now let's say I'm giving you a question which goes like CO EN 3 plus. Guys, you have to tell me the primary valence of the compound and the secondary valence of the compound. Do this, then M EDTA primary valency of M and secondary valency of the central metal atom. Find this out. And the last one is NiOH 2 minus. The primary valency again and the secondary valency of the compound. Try it now. Pause the video and try it. Okay, all of you try this question. Now let's see how much did you get out of 3. Okay, primary valency of this metal. See guys, ethylene diamine is abbreviated as EN and it's a neutral ligand. That means the charge on the species is +3. So guys, the equation can be coming as x plus 0 equals to +3, isn't it? Like if you don't go for the arithmetic segment, simply if you think the charge on the coordination sphere is not given by the ethylene diamine system. That means the charge is responsible, like the metal is responsible for the charge. So x is +3. So that means primary valence is +3. Same as the oxidation number like we do. Secondary valency, guys, 3 elements, so 3. Simple. Now you go for again primary valency. Primary valency over here is again guys EDTA, ethylene diamine tetraacetate. Okay, I'm very sorry, made it -2. My mistake, guys. Again, pause this question and solve this again. Make the corrections. Done. Now have a look. EDTA. If you notice, guys, in EDTA, tetraacetate, 4 minus charges were there. So the number of charge on EDTA is -4. So guys, this is x. X minus 4 is causing the -2 charge on the complex. So guys, x would be -2 plus. The charge on x is +2. The primary valence is +2. That's answer. Secondary valency over here, only one coordination compound. So this is only one ligand. So now let's go for the third question, primary valency. Okay. For this question, this molecule, the primary valency over here is coming as, for nickel, you can see that it is, okay, Ni, it is X. Achha, oxalate, guys, oxalate, it's a -2. -2 system, right? So X -2 is equals to -2. So X is 0. So the nickel over here is 0. What about the secondary valency? Over here is 1. That's your answer. So if you have got this, then your answers are all wrong. Right, you heard me right. Your answers are all wrong. Why is it wrong, guys? Primary valences are all fine. But look at the secondary valences. The answers that we got for secondary valences are 100%. Why is that wrong? Ethylene diamine. What is the structure, guys? CH2, CH2, NH2, NH2. That means one molecule has two donor sites. That means one molecule is equivalent to two ammonia, isn't it? So one ligand is equivalent to one bidentate ligand. Bidentate ligand. Can I not say that it is equivalent to two monodentate ligands? I can, na? So as a result, guys, 3 ethylene diamines has a secondary valency of 3, 1, each of them are bidentate, so total is 6. Here, what is the secondary valency, guys? It is a hexadentate ligand, so the secondary valency is 6. See, it's not about the number of ligands you have. It's about how many bonds is the central metal atom showing. How many connectivity is the central metal atom showing. To accommodate one EDTA molecule inside your compound, guys, you have to show 6 valencies, right? Only then you can accommodate all the 6 centers of EDTA. It's a hexadentate ligand, right? I'm going to show you one example of it. So, it's a 6. About this, oxalate is a bidentate ligand, so it's going to be 2. This is a very minute part test. Let me show you the M-EDTA complex here now. Let's say I want to make a M-EDTA complex. First, guys, you tell me from our earlier discussion, EDTA being a hexadentate ligand, the coordination number is 6. Or secondary valence is 6. That means what is the geometry? What's going to be the geometry? The geometry is going to be octahedral. So let's draw an octahedral shape. Like the square, and then my metal inside 1, 2. I hope you haven't forgotten how to draw the octahedral shapes from coordination compound. From bonding, right? Now this part is important, guys. How do I connect all the EDTA centers? So let's draw the EDTA complex in the right hand side once. Ethylene. Don't wait for me, you try to draw it on your own. Diamine. Don't add the hydrogens in there, just give nitrogens. Tetraacetate. C-double-O minus. C-double-O minus. C-double-O minus. And CH2C-double-O minus, right, guys? Just 1 second. Yeah. Now, let's number them up. Carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, carbon number 7, carbon number 8. Okay? I'm numbering them out, guys, for your convenience only. Now see, this is the nitrogen I'm gonna draw first. This is one of the donor site. This is the other donor site, right? There you go. Now they are connected with CH2, CH2. These two CH2 they are connected with. So let's write one CH2 here and the other CH2. This much we are fine, guys. So this is my ethylene diamine sector. We have drawn. Tetraacetate. Now, in acetate, oxygens are the donor atoms. 4 oxygens are donor atoms. So all the corners you have oxygens because they are the donations. Now, these are the donations. They're all donating. O minuses. Now, guys, let's start with this. Let's say this is the oxygen over here. This one. Now, this is connected to carbon number 1. So let's draw carbon number 1 here. Double bonded 1. This is my carbon number 1. Then carbon number 1 is connected to carbon number 2. Let's draw carbon number 2 now. Then carbon number 2 is connected to a nitrogen. Just connected to it. There we go. Let's do the same thing again. Let's now draw this oxygen here. This is my oxygen. That is connected to carbon number 3. So carbon number 3. that is connected to carbon number 4. So carbon number 4 is connected with nitrogen. Repeat the same thing in this side. That's your metal ADTA complex. Do you see that one compound, one ligand is actually taking over all the 6 centers? So you can be confident now that this is your overall coordination of many details. Let's say we are trying to draw that was an MEDTA. Let's say we are drawing MEN3 complex, ethylene diamine complex. How would you do it? Ethylene diamine is a bidentate ligand. 3 of them are there, so total coordination number is 6. That means it's an octahedral system. Correct, guys? Pay attention in this part. So here is your metal. Again, draw 6 bonds like this. Then after that, you draw the ethylene. Ethylene diamine looks like this. Both of them are gonna be donating. So NH2, NH2, 2 donor sides. CH2, CH2. This is one ethylene diamine. I have to draw 3 of them. Then now 2 connect these 2 corners. CH2, CH2. This. Now you connect these 2 corners. Are we getting this, guys? See how is it hexadentate? How is it bidentate? 3 of them making a octahedral complex. Similarly, the oxalate and everything can be drawn in this way. Okay, clear, everyone? Now, give a heading. Of chelation, or sometimes people call it chelation as well. Chelation. Chelation is something, guys, which is called the crab's claw. Crab's claw. The way a crab looks like, the crab's claw looks like, right? How does a crab look like? It's a beautiful crab, isn't it, guys? Okay, now I have to draw the legs out. Okay, that's your crab leg. The way a crab looks, and the way the crab's claw, that's called the chelation. The way a crab holds something, that's called a chelation. So, guys, why do they compare it with crab's claw? What is it actually? What is the chelation thing? Whenever we have a polydentate ligand, let's say a metal, if you notice the way it was connected with the ethylene diamine complex, right? Let's say I have an ethylene diamine complex. Doesn't it look like the ethylene diamine complexes, 2 nitrogens, are holding the metal in the same way a crab holds the metal? So that's why, guys, this particular thing is called chelation. So what is the chelation then? How would you define it? Polydentate ligands, dentate ligand combined with the metal to form a ring-like structure. To form a ring-like structure, which is known as chelation. This ring-like structure formation is called as the chelation. and chelate complex are the ring formed complexes. Like example, what is the chelated complex? Example, MEDTA is definitely a chelated complex because you have polydentate ligands in here. MOX is definitely a, I'm not putting the charges on that, guys. I'm just giving an example. M-ethylene diamine. So anytime you have connected with, anytime you are connected with a polydentate ligand, guys, it's going to be called as a chelated complex. This is all about. Okay, all right, we're all clear? No doubts? Okay. Now again, guys, we go for a short break. We're done with the ligand segment. We are done with the bonding. I mean, sorry, not the bonding. We're done with the Werner's theory. The next thing that we are going to go and talk about is the IUPAC nomenclature. After that, guys, we're going to talk about the bonding, and we'll be ending this thing up with the isomerism and different small subtopics are also there, guys, like color of a coordination complex and this and that. That also we're going to come out. Take a short break of 5 minutes and then come back, and then we continue with this part. Okay. Right, guys, here we go again. So I hope it has been a long time since we are going through this topic now, and you've understood every single thing I taught you. If there is any doubts, like I said before as well, guys. All right, now, so here we go again. I hope you guys are understanding every single thing that I'm teaching you here. Now, if you have any doubts, like I said, guys, you can always reach out to us through the mails that you have, through the support WhatsApp number. You have my WhatsApp number, and if you're somebody who's just watching the video, who's not a part of Ask IITians, in that case, guys, you can definitely put your comment on the comment section. All right, I'll be definitely replying back to that. So far, guys, we have been learning about all these things about the ligands and how they work, the bidentate, monodentate, all the kinds of ligands which are there. Now, in this part of the chapter, we're going to talk about all the kinds of nomenclature which are there. But before we do that, I'm going to show you the segments that I have already taught you from this chapter here. So this part is yet to be covered up. Okay, guys, oxidation number of the central atom. I think we call it primary valency, and shown you how to do this. Let's say for this compound, let's quickly figure it out. Copper, that is X. Oxidation number of the central atom. Always we do the find out the valency, primary valency and oxidation number are the same thing. Okay, always we do it for the central atom. So let's take it as X. Cyanide is, guys, -1, so -4. Overall charge on the complex is -3, so write it -3. X is coming as +1. That's the right answer. Correct? Simple. Okay, about one thing, homoleptic and heteroleptic complexes. Guys, you have noticed that there are some coordination compounds, those who have only one type of ligand, which is ammonia. They are called the homoleptic complexes. And if you have more than one kind of ligands, then that's called heteroleptic complexes. 2 or 3 or 5 or 6, whatever the number of ligands that you have. If they are same, they're homoleptic. If they are different, then heteroleptic. This part I have already taught you guys how the coordination compound of the coordination number of the secondary valency decides the structure, the shape, right? For 5 coordination number, you have trigonal bipyramidal. For 6 coordination number, for 4 coordination number, you have square planar. For 4 coordination number, you have tetrahedral as well. For 6 coordination number, you have octahedral. Square pyramidal, you are barely gonna see it. Also, the 5 coordination number can give you that. So, guys, in ICO, this complex, if I ask you what is the shape of this compound, you're gonna say, sir, it is either gonna be square planar or it's gonna be tetrahedral. You cannot say anything about it. They are writing that it's tetrahedral because they know the bonding part. You are gonna know about it as well in next 15 minutes. Not 15, 30 minutes actually. This guy, it can be square planar, it can be tetrahedral, right? You can see the answer is square planar anyway here, right? So that's the main thing, okay? Now, coordination sphere, guys, I told you this part of the coordination chemistry, square bracket 1, it's called the coordination sphere, right? Like in code efficiency, what is the coordination sphere? This part. In the coordination entity or sphere are the same thing. I used to call it coordination entity all this time, right? That's it. Apart from that, guys, coordination number, that's secondary valency. I think I've told you this before as well. Like COEN3, guys, EN is a bidentate ligand. So 3 means 3 into 2, total coordination number will be 6 over here, right? I guess it should be written the coordination number for both. Similarly, then the coordination compound, this is oxalate C2O42 minus, guys. This is also 6 because it's the bidentate ligand and 3 of them are there. So the coordination number is 6, as you can see. For both. Ethylene diamine can also be written as ethane 1,2-diamine. Same thing, guys. Ethane in the 1 and the 2 carbon, you have diamine. This is the ambidentate ligand, guys. Okay. Thiocyanide, isothiocyanate. There is something you'll notice. They're writing thiocyanate to S. S means this thiocyanate need 2. A 2 word is being taught in the nomenclature segment that I'm going to show you today. S means, guys, sulfur is the donor atom. N means nitrogen is the donor side. With that, they can make you understand about it. Okay, this is the ambidentate part. Okay, now moving on from there, this is EDTA complex. We have learned about this, right, guys? Hexadentate ligands. I've learned about it. And the type of ligands are being. Didentate means bidentate. Under that, guys, all the examples, ethylene diamine we have done, oxalate we have done, glycinate, I guess they have not mentioned, but that is also there. Okay, EDTA 4 minus, I have mentioned that it is a -4 overall chart. So guys, so far you can clearly see that every single things have been covered up. Okay, central metal atom, what is a central atom? You know, these are the central atom, right? Coordination entity, same thing, coordination sphere, coordination. Okay, yeah. So all these things are done, guys. Now let's come to the nomenclature segment. Okay. IUPAC nomenclature. Okay, guys, no need to study this part from the NCERT over here. Just remember whatever I'm telling you, that's more than enough. It's a shortcut way I'm showing. Okay, the rules goes like this. 1, always write the names of cation first, followed by the anions. Guys, no one is gonna ask you write the IUPAC nomenclature rules, right? So it's your understanding that matters. Okay, not the exact terminology of the words here. Always write the name of the cations first, then the anions. Guys, this is something that you knew for so long, right? KCl, potassium chloride. Potassium first, then chloride, right? Like that. So let's say we are gonna keep some spaces over here. You don't write the things right now, guys. Okay. Later you write it because there are some spaces we need because we'll be discussing that in the end. But why am I keeping the spaces here? Now the next point is, go to the second point. When the coordination sphere is being named. So while naming the coordination sphere, what do we have to remember, guys? The order of naming goes like, the order of naming goes like 1. So first you're gonna name the ligands or ligands with number, means 1 ligand, 2 ligand, 3 ligand. Like let's say I have 6 ammonia, so hexaamine in that, right? Hexa, that is the number. Tetraamine, tetrachloride, like the number you have to mention. That's first. Okay, then followed by the name of the metal. So first ligands with number, then the metals. Now let's talk about the cases here. Case A. In case of multiple ligands, let's say you have a heteroleptic complex, you have more than one ligands. So which ligand are you gonna name first? So in case of multiple ligands, the priority of naming, so whose name would come first, goes by or follows alphabetical order. Alphabetical order. Okay. It would always follow the alphabetical order. So examples are gonna come in the end, guys. Okay, there are few things I'm gonna teach you first, and then you can name the compound. So keep some spaces. Point number B. If the coordination sphere is neutral or cation. That means, guys, if the coordination sphere overall charge is positive or neutral, no charges. In that case, the name of the metal are taken as it is. That means if you have iron, you call it iron. If you have platinum, you call it platinum. If you have silver, you call it silver, as it is. Now I am mentioning that. That means, guys, you can understand something else is coming for the anionic systems, right? But if the sphere, coordination sphere, is anionic, if it is anionic, then what would happen? Then we use the original, the way, from origin of the compound, the way we name it. Like for iron, we use the Fe. Fe is coming from ferrous, right? So if you use the ferrous term now, you cannot use iron anymore. Platinum anyway, like colloquial word is also platinum, original name is also platinum. Forget about that. But let's say we talk about Hg. Hg is called mercury. We call it mercury. We can use mercury if it is cationic or neutral. But if it is anionic, we have to use the original name, that is hydrogyrum, tungsten, wolfram. So you have to use the Latin or the German or the origin name, whatever is being given. With the original name alongside, that's not it, guys. Alongside, what you have to do? Alongside 8 as suffix. Now, guys, you should have seen it come. If it's an anion, you should end it with an 8. 8, or right, but here we only go for 8. That's the thing. Okay. You'll note it down. Later on, I'm going to give you all the examples all together. Now, every anionic ligands, those ending, so you go like this, anionic ligands ending with suffix 8, ite, or ite, 8, ite, or ite, is modified as ito, or ido. So, guys, it's like E gets modified with O. Now, why do we do that? What is the logical reason why? Just to show them that this is a coordination compound. This is the only part, guys, that can make them understand that we are talking about a coordination compound. Like examples here onwards, we can give the examples here. Now, let me give you all the examples all together now. Example. Cl minus. What is its name, guys? Chloride. But it ends with ite. Ite cannot be ite. It would be ido. E changes with O. So, guys, we are gonna call it chlorido. Chlorido. Let's say I minus. What am I gonna call it, guys? Iodide. So iodido. Iotido. Let's say SO4 2 minus. What is its name? Sulfate. But E turns with O. Sulfato. Cn minus. Anionic ligand. Cyanido. Cyanido. Water. What do we call it? Watero? No. Water is like, we call it like aqua. Okay, so from aqua, it's gonna be called as aquo. Right? Wrong. Why wrong? Because it is not an anionic ligand, guys. It's a neutral ligand, right? So we call it aqua. No change in name. See, you still not see. Aqua. NH3, guys. Amine, right? Amine, ammonia, but as a inorganic also you call it amine, right? Like the chapter name is amine. Remember, nitrogenous compound is called amine. So when it attaches with somebody, it's called amine. But here, what are we gonna call it? Amino? No, it's a neutral system, so no amino. It's only amine. A-M-M-I-N-E. Only for anionic systems we change it, right? Let's write it one more time now. Let's say, guys, I have given you CO, not cobalt. CO. What do we call it? Carbon monoxide? No. CO over here is called carbonyl and it's a neutral ligand. So we're gonna keep it carbonyl. Right? Let's say one last question, guys. Let's say we call it. Let's say we go for OH minus. What am I gonna call it? Anionic. Hydroxide. Hydroxido. Now you try this one. Cn minus. In Cn minus, guys, I have told you specifically the minus charge is on carbon. Remember that always. Okay. What am I gonna call this one? Cyanide. I have already written it, right? But still, I'm gonna modify it once. It's gonna be called as cyanido. Generally, whenever you say cyanido, okay, no need to write it, guys. What I meant is if you have written NC. N triple bond C. In N triple bond C, you have a minus charge on carbon, but the lone pair of nitrogen is being given. I meant this one. It is called isocyanide, so isocyanide. That. Okay, let's say, guys, you have NO2. Now this one is special. NO2 is also an ambidentate ligand, you know. It can be donated from here or from here, or not and. And if it was and, then I would have been calling it bidentate. But I'm writing or, that means it's an ambidentate. If it is donated from this side, what am I gonna call it? It's called nitrite, right, guys? Nitrite, not nitrate. Nitrate is NO3, NO2 minus nitrite. Nitrito. But who's that donor atom? N. So I'm gonna write nitrito N. But if oxygen was the donor atom, if I had a system where oxygen is the donor atom here, in this case, guys, we call it nitrito O, like that. I would suggest you to go through all the names of the donor atoms, guys. Just check it once. From here, from the NCERT, there is a list given. There should have been a list given by them. Okay, I believe they haven't given any list, right? There was one. So 48, 59. Is there any pages missing? 251. No, they're not giving lists. Okay. Anyways, guys, I have told you. Mostly I've told you all the names. So as there is no such lists present, so I'm gonna tell you a few more then. Okay. Let's go for this. Let's say we have one more ligand. Let's go for CO3 2 minus. CO3 2 minus is called carbonate, right, guys? So we're gonna call it carbonato. Carbonato. Every time we end with an E, it would be turned into O. Only if it is a anionic ligand. Only then, guys. Okay. Let's say En. What is En, guys? The bidentate ligand. Ethylene diamine. I'm gonna keep it as it is. Ethylene. Okay, they can call it another way. Ethane 1,2 diamine. Same thing, guys. Nothing to change about it. 1,2 diamine. Same thing. Just keep some spaces between them. Diamine. Ethylene diamine or ethane diamine. Same thing. GLY. Guys, glycine molecule had a negative charge if you remember, right? So glycinato. OX. C2O4 2 minus. OX. So oxalate, oxalato. Oxalato. More or less these ones would work. Okay, if you let's just solve a few questions. If I see anything new coming in, then I'm gonna mention about that, right? Okay, let's go for the other examples over here, guys, quickly. Okay, a coordination sphere is a neutral or cationic. Let's start from the beginning, then we'll come over here. All the examples, right? Always name the cation first. No. Let's not do there. Let's start from here only. Okay, if a coordination sphere is a neutral or cationic, the name of the metal taken as it is. Let's say, guys, I have a coordination sphere which goes like this. CO, NH3, whole 6, 3 plus. What am I gonna call it? It's gonna be called as, I'm writing it down below. It's gonna be called as, yeah. First, if you just notice the point before that, in case of multiple ligand, no, not here, here. The way we name the compounds. Here, go here first. When the coordination sphere is being named, we start with the ligands with number and then metal. Like let's say the same example, if I try to go for CO, NH3, whole 6, 3 plus. That was the example that I was writing. If I want to name this thing, guys, how am I gonna start? First ligands with number. So hexa, amine, not amino, amine, neutral ligand, no changes. Hexamine. Then after that, the metal name. The metal name would be cobalt. So hexamine cobalt, iron. That's how we name it. Okay, because it's an ionic compound, so we're gonna call it. Okay. Here in that way, what I'm gonna show in here, guys. So this one is same. Hexamine cobalt, iron. As you have noticed, guys, it is a cationic ligand. That's why, like I said, the name of the metal are taken as it is, not each. But let's say I'm giving you another example. Let's say you have FeCN whole 6, 3. What are we gonna call this compound? Hexa. Now CN is cyanide. In this chapter, cyanido. Then, okay. Sorry, we have taken a negatively charged system. If it is a negatively charged system, guys, an ionic ligand, we use the original name alongside it. Original name of the metal is iron, is the one that we use. Ferrous or ferric is the word that is the original with an 8. So hexacyanido, ferrate is the name of this one. Iron. Don't forget to put the iron name, guys, on the top of it. If it's an ionic compound, make sure that you write the iron word. Okay. Keep a space between them, a big space. We're gonna add another thing in between. Keep a big space. Okay. Here also, keep a space. Let's go for another one. Cu, NH3, whole 6 plus. What are we gonna call this? This guy is gonna be called as hexaamine copper. Right? Let's say we have another complex which goes like PT, CN6, 4 minus. What is going to be the naming of this compound? Hexa Cyanido platinum. Correct, guys? Any doubts so far? Any doubts? There should be one doubt. Sir, why is it platinum? It is a negatively charged. So should I call it platinum? No. I should call it platinate. 8 with the original name. PT is the original name anyway, platinum, right? Okay, so that's how we name these compounds, guys. Okay. For the anionic and the cation. Okay. In case of multiple ligands, how do we go for these examples, guys? In case of multiple ligands, let's say I have a question which goes like this. CO NH3 whole 2 Cl2 Br. Okay, let's say there is a question for a compound like that. What are we gonna call this guy? Yes. Just 1 second. 2 to 4. This is a compound. So what should be the name of this compound? So we are gonna go like the ligands first with the alphabetical order. The name of NH3 is amine. The name of Cl is chlorido. Anionic is Br is bromido. Tell me alphabetically what comes first. Definitely A, C and B. A, then B, then C. The name. Diamine. You can start with a capital as well, guys, no issues. Diamine. Dibromido. Dichlorido. Then anion, cobaltate. Okay, you try one. Cu H2O whole 2 Cl2 NO2. Okay, go for ONO. ONO. Let's add another one. ONO. I. This is a compound given to you. So the names first. H2O is aqua. I hope you haven't forgotten it. Aqua. Cl is chlorido. ONO. Nitrito. O. Because you can see the connecting atom is O. O is written first. If the connecting atom was N, NO2, I would have been writing NO2. I'm writing ONO. That means O is the connecting atom. I is, guys, iodido. So the name of this compound would be diaqua. Then dichlorido. Nitrito. O. Iodido. Now charge. Let me give a charge. 3, 1, 4, 1, 5, 2, 1, 3, 1, 4, 2, minus 2. Iodido. Cuprate. Cuprate. Right? That is the name of this compound. Okay, guys. Now, the last thing about the naming. How many rules have I taught you so far? C. Okay. 2C. 3. Every naming should have the name, of the primary valency. Primary valency of the central metal atom written in Roman letters. written in Roman letters inside a first bracket beside its name. That means, guys, every single time whenever you have named it, it was incomplete. What you have to write is, every single time you have to write the Roman letter primary valency beside it. So let's say this is the coordination sphere. Okay, the central metal atom would be this guy. So what is the primary valency of this guy over here, guys? Figure it out. X0 plus 3. So x plus 0 equals to plus 3. So x equals to plus 3. So hexamine cobalt in Roman letters Pi. Then x minus 6 equals to, so x minus 6 equals to minus 3. That means x would be plus 3. So from there, guys, primary valence or oxidation number, same thing. About this guy, hexamine copper iron. The moment you have written copper, you have to show the primary valence is 1 iron. Hexacyanidoplatinate. Hexacyanidoplatinate. So here, guys, PT. What is the valence of PT? X minus 6 equals to minus 4. That means okay, I forgot to write iron. See, there was a mistake there, right? So similarly, guys, keep on going with the names here. Wherever you have a name, you write down the primary valence beside it. The moment you write that name, see, diamine, dichloride, dibromate, cobalt. Cobaltate, I have written cobaltate. After that, the primary valence. Write it down now. X0 minus 1 minus 1 minus 2 total minus 2 total. So x minus 4 equals to minus 2. This charge right here. So x would be equals to plus. That is it. Right after you write the cobalt, the central metal atom names, right after that. Copper over here. 0, minus 1, minus 1, minus 1. ONO or NO2 has a minus 1 charge, right? So x minus 3 equals to minus 2, x comes as plus 1. So, right? So this is the thing. Now, guys, here what would happen? Figure it out. It would be plus 3 because ammonia is anyway, it's a neutral ligand. So, guys, we have given all the examples of every single thing now. The nomenclature thing, I guess it is very, very clear to all of you. Now, there is one thing that I haven't given example for, is this one. So, guys, all the time we were considering the ionic systems. Let's consider some neutral systems here. Let's say K4 FeCN6. No such ions. We are going to name the entire compound here. What would be the name of this guy? So, guys, first you write the name of cation. So what is the cation? Potassium. We write tetrapotassium? The answer is no. We don't. We just write potassium. We don't need to write tetrapotassium because, guys, that we can figure out by primary valency of the central metal atom. That's why I'm going to show you how. Potassium. Then the coordination entity starts. The coordination entity is my anion over here, right, guys? This is my cation, this is my anion, because the cation is always written first. In the symbol also we write it first, right? So here what would happen? In the anion, it's a coordination sphere. So, guys, hexacyanido. We're gonna start with the ligands. Hexacyanido. Then iron or ferrate. Ferrate. Because it's an anionic. Ferrate. Is it over? No. You have to give the charge of it. How do you find out the charge, guys? How do you find the primary valence of the oxidation state? Take it as X. Each of the potassiums are plus 1. Each of the cyanides are minus 1. So, plus 4 plus x minus 6 equals to overall charge is 0. So, guys, the x is coming as plus 2. No such ions you need to write because you have neutral system here. Okay, let's try one more now. Let's say you have CuNH3 whole 6 SO4. How are you going to name this one? Here, guys, the cation is a coordination compound. Correct? So you now start with that name. Hexaamine. Hexaamine. Copper, not cuprate. It's a cation, copper. Then the primary valency, I'm going to keep it for later. sulfate. Now what is the primary valency? Quickly figure it out. You take it as X, this is 0, this is -2. We know that sulfate is -2, right? So X minus 2 equals to 0. That's it. That's how you name the complexes. Now we are going to try to name another complex here. Let's say, guys, they have given you a question where Fe(H2O) whole 6 and FeCl. That means both the cation and the anion is your coordination compound. Then how are we going to do this? Hexa aqua iron, normal name. Keep spaces for the primary valence. Then hexa cyanido ferrate, not iron, it's time, ferrate. Now the primary valence is, guys, take it as X, 0, X minus 1. That means 2X minus 6 equals to 0. X is coming as +3. So each of them are 3. That's how we do it. Okay. So this is how you name these compounds. Am I missing out anything? No, I guess we have covered up all the cases here, right? That would be all of the cases. Now, guys, let's try to figure out the other way around. Okay, let's say they have given you the names and you have to figure out the structures for this part, let's say. Let's solve a few questions from here. Next question. Tetraamine diaqua cobalt chloride. That means this part is my cation, this part is my anion. This part is clear? So first you write the coordinations here, then you write chloride. But how many chloride you don't know. Like I told you, no? Counter ion, they don't mention the number. That you can find out very easily. Let me show you. Tetraamine diaqua cobalt. So the central metal atom is cobalt. With that you have 4 amine and 2 water. The primary valence is given as 3. That means if it is +3, guys, this is 0, this is 0. So the overall charge on the coordination sphere will also be +3. That means how many chloride do you need, guys? That's how you can find it out. Let's try another one. Potassium tetracyanidonickellate. Acha, that means potassium is the cation, this is my anion. So you write potassium, but how many potassium you don't know. Tetracyanidonickellate. So write nickel and coordination number 4. Tetracyanidon. Nickel has a +2 charge. So let's put a +2 in here. Now cyanide is -4 because 4 of them are there, 1 minus each. So overall charge of the coordination sphere would be +2 minus 4. Overall is -2. So how many potassium do you need, guys? Because 1 potassium is +1. Let's try one last. Acha, tris. This part is yet to teach you. Okay, just one sec. Let's go for one other one, which is not that kind of nomenclature. Amine, bromido, chlorido, nitrito, N, platinate. Okay, let's go for this one. Amine. That means nitrito, platinate. So platinum, nitrito, N, platinate. 2. Acha. That means, guys, it's an anionic system. 8 is given. Platinum. Then you have amine. How many? 1, because they have not written any number. Bromido, bromido, chlorido, chlorido, nitrito N, that means NO2. That's your thing. What is the charge? The platinum is 2. This is 0. This is -1. This is -1. This is -1. Total 2 minus 1. So the total charge on the coordination sphere will be -1. That's how you do this kind of question. This tris. What is this, guys? Whenever you have bidentate ligands like ethylene diamine, in these cases, as the bidentate ligands has already this kind of di, tri inside the names, whenever you have bidentate ligand, tridentate ligands, they use tris rather than tri or di. They use tris, bis, tris, tetra case, a penta case, like that. Tris means three. Three, we don't write like triethylene diamine. For bidentate ligand, we write like tris. It's like oxalate, they were oxalate. So tris oxalate, like that. So tris ethylene diamine chromium, that means chromium is there, 3 times ethylene diamine, and then you have fluoride. How many? See, chromium is in +3 oxidation state as they have mentioned. So ethylene diamines are 0. So overall charge on the thing is +3 then. So chlorine is needed as 3. Like this, how we do this compounds, guys. Okay. In the next class, in the next video, up to this, we are going to end this video here. In the next video, what we are going to do is, guys, we are going to start from the isomerism, bonding, and the rest of the part which are there, the color of the coordination compounds, and rest all of the part, right? So there'll be total 2 segment of this video. So if you need till the UPSC, this is where it ends. And in the next video, guys, we are going to complete the rest of the part, and then we are going to solve some questions as well. I hope this video was helpful to you. If you want to solve more questions like the NCERT, guys, you can definitely refer to our module, or you can always go for the different previous year questions. Those are there as well. We are going to solve the PYQs in the end of the second video. Okay, so we are going to keep it up to this for today, guys. So bye bye. We're going to meet you in the next part. Make sure you watch that part, guys, after you watch this part. Okay, from there we are going to start from the isomerism segment, and the isomerism we need the names, guys. Okay, so see you in the next session then. Bye everyone.